Okay. Have the licensing issues corrected, at least for now. Oh, let me turn the projector on. Yep. So returning to our example here, we had the distribution center location. We had 10 city locations where we wanted to ship or travel to from the distribution center. So we just wanted to minimize the sum of distances from the distribution center to each of the 10 cities. So that's what we have computed here in D12, which is our objective we want to minimize. And so we have, in this case, some solution, 0, 0 inputted. If I run the solver, so I will again show that I've selected the large-scale, generalized, reduced gradient, nonlinear engine. So the key is it's nonlinear. And if I run that solver, we'll get, in this case, a green message saying it found a solution, all constraints and optimality conditions are satisfied, which simply means for the nonlinear solver that it found a local optimum. Right? This isn't guaranteed that this is the best answer, but it's the best answer close to the decision variable values. So there was no value near these that was any better than this. So 114 and 35 gives us a total sum of distances of about 670. Just out of curiosity, I'm going to paste these so we can remember them, and I'm going to rerun the optimizer from a different starting point. So let's imagine if I started from 200, 0 and reran the same algorithm, same model and everything, just a different starting solution. Let's see if it gets any better of a answer. Looks like it converged back to the same one. So let's try maybe 0 and 200 just as some examples, and assert that even searching from that starting point gave us a best answer. Now, because of the way we're only using technically quadratic functions, squares and square roots, there shouldn't necessarily be lots of hills and valleys in this objective function. It should overall be very convex, meaning there likely only is one hill to climb. And so even from different starting points, it comes back to the same solution each time, which increases our confidence that this may in fact be the best global solution, the best global optimum as well. Okay, so let's move on and talk about another kind of problem. So that was our first example of nonlinear optimization. Let's look at one more. In this case, we have a telephone company that supplies long-distance telephone services. I don't even know that these still exist these days, but let's imagine they do. So you have to pay a company to be able to call long distance on your home phone. And they have two different rates, that is, price per minute that they charge. One for daytime, which they defined as 8 a.m. to 6 p.m., and one for evening, which is the opposite, everything else. Okay. And they've estimated that there's a certain amount of demand or usage of long distance. And so we have a few equations here that represent how demand changes based on the prices. So I've laid it out with some acronyms here. Daytime demand is DD, evening demand is ED, and then so forth for price. So the equation here of daytime demand says that there's a base demand of 600 minutes that people will call long distance during the daytime. However, that demand goes down, so minus, goes down for every increase in our daytime price. That is, the more we charge people for calling during the day, the less likely they are to do so. The less of them, or the less time they spend on the phone during the day. However, daytime demand increases when the evening price, the price for calling in the evening, increases. So if it's more expensive to call in the evening, people are more likely to call during the daytime. And so forth for evening demand. So evening demand has some base 400, say, minutes, plus 600 minutes for every $1 increase in the daytime price, minus 2,500 minutes for every $1 increase in the evening price. So when evening price is increased, we charge more. people are less likely to call in the evening, more likely to call in the daytime. Okay, our revenue, something like this. So 600 units, let's say, times the daytime demand times the daytime price. Okay, plus 400 times evening demand plus evening price. Okay, so these are just the equations given. So we want to maximize this revenue subject to all we can choose. We don't get to choose demand. What we get to choose is the price, daytime price and evening price. So again, I'm going to jump into Excel. I've already set up an Excel sheet with these parameters typed in. So the base demand, the adjustment to the daytime demand for each daytime and evening unit or price increase, and then the evening demand price adjustment. Okay, so our decision is the price of a minute for calling during the daytime. So I don't know, let's say that's 10 cents, and evening is let's say 8 cents. Okay, so that's just going to be a starting point guess. Oops, not what I clicked. Make these dollar amounts, and because there are decisions, we'll mark them with orange. Okay, and our revenue, if you remember, let's do our calculated demand. So the demand of daytime units is the base demand plus this adjustment, okay, negative 5,000 multiplied by the price of a daytime minute. So for every dollar of cost that people would have to pay to call for 1 minute during the daytime, there's likely to be 5,000 less callers, 5,000 less minutes used. Okay, plus the adjustment for the evening price times the evening price. Okay, so again, for every dollar increase in the evening minute, how much that costs, the demand for daytime minutes, that is the people who will call during the daytime, goes up by 600 minutes. Let's say. Okay, so that's the adjusted demand. Let's call that adjusted demand for daytime, and we can do the same for the evening minutes. So there's the base demand plus the daytime price adjust times the daytime price plus the evening price adjust times the evening price. Okay. So now we can compute revenue because we know how many minutes people will call long distance during the day, and we know how much we'll charge them per minute. So it's just the adjusted demand times the decision, and then I believe we also multiplied that by the base demand or by 600, and then so forth for the evening price, which was multiplied by that base unit of 400. Okay, so those are all the equations that just came out of the problem description. And then if we sum the two revenues for what we charge for daytime calling and evening calling, that is our total revenue, which is our objective we'd like to maximize. So we're going to maximize our revenue by setting prices such that our demand is high enough, right, that the charge per minute for all that demand leads to a higher revenue. Right? We could charge a very large amount of daytime minutes, let's say a whole dollar, okay, but that's actually going to lead to people not wanting to call during the day whatsoever, right? An actual negative value, which will lead to a large negative revenue, right? So obviously that wouldn't be what we'd want to do. So we may want to try something more along maybe 12 cents, okay? Or maybe we'd like to go even lower, maybe 5 cents, okay, and so forth. So we're going to use a nonlinear solver to solve this equation. Now the reason why, again, it's nonlinear is because the objective here involves the decision variable multiplied by the adjusted demand, which also involves both decision variables. Okay, so even though the adjusted demand is a linear function and this revenue function looks linear, this revenue function is technically multiplying one decision variable by a formula that already involves decision variables. So we're going to end up with squared decision variable terms. Does that make sense? I want to make sure the reason why this is nonlinear is clear. So our objective, revenue, whether it's daytime or evening, either one, involves the decision variable multiplied by something else, and that something else also involves, in this case, both decision variables. So we have decision variables multiplied by one another in some cases. So definitely not linear. Okay. So all we have to do is mark the decision variables as our decision variables and mark the objective as what we're trying to maximize. Okay. Again, it wouldn't make sense conceptually for the decision variables to be negative. Right? Why would we give people, say, 1 cent back for every daytime minute they call? Right? That doesn't make sense from a marketing standpoint or telephone standpoint. But if we made such a decision, it would lead to a lower revenue, right? Because we're giving back money instead of charging money. So the optimal solution should not involve negative values, even without us having to constrain it and tell it not to use negative values. Okay? So I'm not going to worry about adding a constraint to say these must be positive or 0 or greater, or even the assumed non-negative parameter to the model or the engine. Okay? Because it wouldn't make sense that a optimal solution would ever involve negative values anyway. It's not going to try those, or if it tries, it will soon learn those are not going to be good values. Okay? So let's run the model. Okay. So again, we see that it says it found a solution. All optimality, or all constraints and optimality conditions are satisfied. And what it found was we can earn revenue of almost $20,000 by using a 7-cent daytime minute and a 10-cent evening minute. Okay. So we're going to charge a little more for the evening minutes to sort of drive either more demand into the daytime, or possibly because of these parameters up here tend to favor, right, lower daytime hours or lower daytime costs than they do lower evening costs. Okay, so it's better for revenue if we charge less in the daytime than we do in the evening. Okay, and this particular set of values is what led to the optimal solution that was found, which is almost 20,000. Again, we could start it from different starting points. So I think I had 5 and 10 cents anyway. Let's try 12 cents and 1 cent, and we can rerun. But because this problem is mostly convex, involves squared values only, really, it's pretty well constrained to have only one hill to climb. There's not multiple local optimums. There's really only one optimum, which happens to be the global, and that's this one here. Okay. All right, so that's another example. Let's look at another. So let's imagine we were a pharmacy drugstore chain. We have 10 pharmacy stores in our chain. Okay, they're open for different numbers of hours. So some of them may be freestanding buildings. Some of them may be inside of other department stores or things like that. And so the hours they are open is different between each store, and we each earns a different average revenue that we've measured. So how much money did that store bring in? And what we want to know is there a sensible model for predicting revenue from hours, such that it may look like this? Okay, so is there some good values for some value A and B, such that A times the number of hours raised to the B power is a good estimate for how much revenue that store would have? Okay, if we could build a model by some function like this, which was accurate for this set of data, these 10 stores, that would help us make decisions about how many hours each store should be open, because we could predict how much more or less revenue it would earn. Okay, because we'd have this model, this equation with an A and a B value filled out that would tell us how to predict revenue from hours alone. Okay, so we're going to start with these 10 sets of data. Okay, what we're going to do is we're going to compute an estimated revenue using a function like this, and we're going to compare that estimated revenue with the real revenue, what we actually have recorded. And what we want to do is pick A and B values, so those are our decision variables. We're going to pick an A and a B value to minimize our error. That is, how many times we predict a revenue that's different, or how off of a prediction we make of the revenue from the real thing. Okay, so let's go back to Excel. So here I have that same set of data, 10 stores, number of hours open, and revenue, which is supposed to be currency. Okay. And what I'm going to do, and make some space here at the top for doing this. So we're going to have some model parameters, parameter A and a parameter B. And I don't know what A and B should be, so I'm just going to use 1 and 1 for both of those to start with. And those are going to be our decision variables. So we're going to try to find values for A and B. Okay, that's what we're going to decide. Now what we're going to do with those A and B values is we're going to compute for each store A times number of hours raised to the power of B. Okay, and I'm going to make the A and B cell references to be absolute. Okay, so you can see the equation there. So that is my predicted revenue. Okay, so in this case, A and B values both being 1 means we'd predict revenue of 40 for store 1. And if I copy that down, you can see what value it has for all the others. Okay, so that's my prediction. That is, I'm building a model where I'm going to choose A and B values to predict revenue from hours. And what I'm interested in, okay, is the error. That is, the difference between the actual revenue and my prediction. Okay, so this should remind you of short-term forecasting, where we were predicting values and then we were interested in the error, how off our prediction was. However, in this case, what we're going to do is we're going to optimize our choice of A and B values. So we're going to use a nonlinear optimizer to choose these values to minimize the errors in our predictions. Okay, oops. So those are all the errors, and because the errors could be positive or negative, what we're going to do is we're going to square all the errors. Okay, so we're going to take each error multiplied by itself and square them, and then we're going to sum all of those squared errors up. Okay, so that just ensures that we don't make a prediction that's an overestimate and one that's an underestimate, and those cancel each other out. That is, a positive and a negative error add up to be zero error. Right? We want to ensure that we always have positive errors that we're summing. Okay, so this sum of squared errors, this should remind you of mean squared error, but that sum of squared errors is going to be our objective. Okay, the sum of squared errors. Okay. Okay. So we'll just format this to look a little nicer. There we go. And now what we want to do is we want to build a nonlinear optimization model where these A and B values are our decision variables, and this sum of squared errors is the objective we want to minimize. So we want to get the smallest error by choosing A and B values that can predict revenue the best. Okay. the most accurately. So let's run the optimizer. Okay, and I'm going to, so it found a solution, a value of 1,022 and some, and a b value of roughly a half, okay, for a sum of squared errors of something like 7.5 million. Okay. However, what I want to point out is the fact that on the solver panel over here, it gives us a different message than it typically has. Instead of saying that all constraints and optimality are satisfied, what it's found is it converged to a good solution, and the constraints, which there aren't any here, are all satisfied, but it has no idea if this is truly the optimal solution. So again, it could be that there might be multiple hills, and it's not sure that it's climbed the tallest one. Okay? That is, there might be better A and B values somewhere else, not close to these, which would give a better sum of squared errors, and the engine itself has been able to detect that and is basically giving us a warning that these are very good values, but not guaranteed to be the best. Okay? And again, that depends so much on the initial values we start from. So I'm just going to try a few different starting points. So we'll remember these values, copy and paste the values down here, and instead of, let's start from 1200 and maybe 0.2. Okay, rerun. Okay, and it looks like it converged back to the same solution it had before. Okay, so maybe let's start from 1100. And let's see if we can get a real low value of B and maybe a very high value of A, such that we would predict with a fair amount of accuracy. Okay, and let's rerun the solver. So a new starting point, and it's converged back to the same one. Okay. So even though it's told us this may not be the best solution, we've tried 3 different times, starting from different places, and it's climbed to the same hill, or in this case it's really going down the valley to the minimum error that it can find. Okay? So that's good. Let's imagine, though, instead of the model being A times the number of hours raised to the B, okay, power, let's imagine we used a log function. Okay? So I'm going to build a totally separate model to the side, where instead of A times number of hours, okay, I'm going to use A plus B times the log of the number of hours. Okay? So maybe for some reason I believe that could give us a better model that would give us better accuracy in prediction. Okay, so instead of a quadratic, or I'm sorry, not a quadratic, instead of a power model where I'm using a power function, I'm using a logarithm function. Okay, so those are my second set of predictions. They have their own error. Okay. Squeeze some of that in. So the difference between the real revenue and the second prediction. So this is error 2. And of course, we'll do the same thing where we square each of these errors and then sum all the squared errors. Okay. So this is a totally separate model. Okay, I'm just going to put a border in between them to make sure that's clear. Okay. And now, instead of using this sum of squared errors as our objective, let's use this sum of squared errors as our objective. So I'm going to reset the objective now to minimize the value in I-15. So I'm going to see on the model here that that's now my objective, minimizing I-15, the sum of squared errors of the second prediction model. Okay, and now I can run. Okay, and what it's found is using a negative A value and a very positive B value, right? It's found some suitably optimal, okay, something it believes is optimal, sum of squared errors. Okay. Now, sum of squared errors is one way, right, we can measure error. If you remember back to forecasting, you can also use things like absolute error. So just take the error value and make an absolute value out of it and sum those. So let's see if we did that, if it would change anything. So this is a different kind of objective now. We're changing our objective from minimizing sum of squared errors to minimizing sum of absolute errors. Okay. So let's remember what we started with. Okay. And rerun. Okay. And it found something of a similar nature, but slightly different. Okay, a slightly less negative A and a slightly less positive B for a different absolute sum of absolute errors. Okay. Now, whether or not the first model, which used power functions, basically raising one value to another, versus the second model, which used logarithms, is better or worse, right? We could compute some of the optimal sum of squared errors or the optimal sum of absolute errors in one and the optimal sum of squared or sum of absolute errors in the other and compare those to see which one was better, okay? Or we might think of new functions we could use, okay? Just out of curiosity, let's create a chart. We'll do a scatter chart. Since these are already in order of hours. So here's what the data points look like. Okay, so you can see there's generally the more hours, the higher the revenue. Okay, but there's some squigglies and there's some sort of up and down between them. So it's not always true that a store with more hours will earn more revenue than a store with less hours. But that's generally true, which might lead us to that conclusion of there could be a way to predict this. Now, whether or not that's a power function or a log function or even a linear function is something, we would have to choose and maybe decide on by ourselves. This was just an example of two kinds of models we might think of for doing that. Okay. So that's 3 nonlinear examples. Let's look at... So we did that. So what if the revenue model was the log of hours instead of hours raised to the power of B? So let's look at another common optimization problem. So one optimization problem that comes up over and over is something called economic order quantity. Okay, so imagine you have some product that you order, you have to pay for, that you stock in your store for selling at a retail store. And what you have to decide is how much of that product do I order to keep up with the demand of people coming in and buying it so I don't sell out and miss opportunities to sell more, but I also minimize the cost of having to find space to hold all those items. So I don't want to order too much. I won't have room for them. And there's an inherent cost with each item that I have to keep in stock. I have to pay somebody to make sure it's out on the shelves in the right place. I have to air condition the building, whatever it is, to keep the product in the right state. So there's some cost with having more product on hand, but there's a missed opportunity for sales if I don't keep enough of it on hand. Okay, does that make sense? So I'm going to decide how much or a quantity of a product to order. subject to a fixed order cost. That is, every time I have to order more product, there's a fixed cost with that. So I can't just keep ordering one product at a time every day. Or I could, but I have to pay overhead every time I order more product. So it would be better if I can order in bulk fewer times and pay less overhead. But there's also a holding cost. That is the cost associated with having product kept on hand, right? Keeping it on the store shelves and whatever else needs to happen to it. Okay, and then of course there's a space constraint on how much is storable at all. So I can't have too much product, or I won't have a place to put it. So let's imagine we're going to let 4 different variables represent these different quantities. So let D be the total demand for the product. That is, maybe it's over the course of a year or a month or whatever it is. I could think I can sell D units of the product. Let's let K be the fixed order cost. So every time I order more, I have to pay K dollars. Okay, plus whatever the unit cost is multiplied by how many I order. Maybe. Okay, and then let H be the holding cost. That is, however many units of a product I keep on hand, over the course of time I have to just pay to upkeep those. Okay, so the holding cost. And then Q be the decision variable, what we're going to decide, which is how many items to order each time we order. Okay, so imagine, so here's just a few simple equations. The ordering cost, that is the fixed order cost, okay, is going to be K, fixed order cost, multiplied by D over Q. Okay, D being the demand, Q being how many items we order each time. So D divided by Q is how many orders we'll make. If we're going to sell 100 units, D is 100, and we're going to order 20 units at a time, then we'll make 5 orders, right, before we've sold up to the demand that we think we can sell. Okay, so the D demand divided by Q is how many orders we'll make. Multiply that by K, and that's your ordering cost. That is how much overhead you pay for making orders. Okay. What's called the inventory cost involves that H, or that holding cost. And this gets a little more complicated because you have to figure out how many items do I have on hand on average. Okay? So when I order Q items, I have Q on hand, but I'm constantly selling them. Eventually I run out or come close to running out and I order more. So the question is, on average, how many items do I have in stock? If we assume that we sell things at a linear rate, then we will order things when we run out and get Q more, and then go some amount of time, sell all those, order Q more, and so forth. If that rate is linear, then on average we have Q over 2 items in our store, right? So day 1 we have Q, day 2 we have 1 less than that, day 3 we have 1 less than that, 1 less each day until we run out. On average, over all those days, we had Q over 2 items. Multiply that by H, and that's your overall inventory cost. That is how much it costs to keep those things in stock. So the average quantity we had multiplied by the holding cost. All right, so here's some real numbers for an example. Okay, so let's say we have 4 products, 1, 2, 3, 4. We know the demand, let's say that's per year, for each one. So we want to sell 5,000 product ones. We want to order 5,000 product ones. That's how many we think we can sell in a year. Each time we order more product one, it costs us $400. Okay. For every product one we keep in stock, we have to pay 10% of the purchase cost. Okay. So if a product one costs $500, 10% of that, or $50, is kind of what we estimate we have to pay just to keep it in stock, keep it in inventory, keep track of it. Like I said, if you have to do some sort of maintenance to keep it clean or clear or stocked on the shelves in the right place, whatever that is, the holding cost per product one is 10% of its purchase cost, $50. And each product one requires 12, let's say these are square feet, 12 square feet of space, okay, and so forth for products 2, 3, and 4. So we know demand, we know fixed ordering cost. Between the holding cost percent and the purchase cost, we know H, the cost per unit, okay? And we know how much space each unit takes, say in our store or our warehouse. The only other thing we need to know is how much space we have available, in this case 12,000 square feet. So what we want to do is create a model that says, I want to figure out how many product 1, 2, 3, and 4 to order to minimize my my costs, ordering costs and holding inventory costs, holding costs. Subject to, I can't order too much, right? If I were just going to minimize costs, I would say order everything one time. It's one fixed order cost. But I don't have enough room to store all that, okay? So I have to find sort of that balance between ordering just enough that I use all my space, but minimize the number of orders I make in order to minimize those costs. Okay. All right. I should have. There we go. So I should have those numbers copied here. So these are our parameters. So we have our decision variable, which is going to be the quantity of each order. Okay. So how many of each product I'm going to order at a time. Okay, so those are our decision variables. In this case, 4 of them, 1 for each product. Okay, and then we're going to have a number of calculations. Okay, so one thing we need to decide is how much ordering cost we're going to pay and how much inventory cost we're going to pay. Okay. But to know that, we need to know first how many orders we're going to make per year. So the count of how many orders, which is, as we said before, the demand divided by the quantity. That is, if I need 5,000 units of product 1 and I only order 10 at a time, I would have to order 500 times throughout the year. Okay? And so forth for all the products. So that's my order count. Let's make that. There we go. What else do I need to know? Well, now that I know how many orders I'm going to make per year, I can compute order cost, which is how many orders I make multiplied by the fixed cost. So if I make 500 orders for product 1 throughout the year, each one costing $400, I have to pay $200,000 in ordering costs. Okay, seems like a lot. Let's format those, as well as these. Okay, so that tells me how much ordering cost. The other thing I need to know is my inventory cost. So again, I need to know how many units of each product do I have on hand on average. And if we assume we sell products at a linear rate, then we'll just say if we order 10 products at a time and only order more when we run out, the day we run out, then we'll have 10/2 or 5 products on hand on average. So we'll start with 10. Eventually we'll get to where we have 0. You know, on average, across however many days that takes, we'll have 5 units of each product on average. Okay, so that's the average inventory. So now we can compute the inventory cost, which is our average inventory times the holding cost. The holding cost here is a percentage that we want to multiply by the purchase cost. Okay, so those two values multiplied by each other is the actual dollar amount of how much it costs us to hold each unit of the product in stock. Okay, so let's make that currency. So by ordering very few products at a time, we have very high ordering costs, but very low inventory costs, right? Because we have very little inventory on hand, okay? So the inventory costs are very low, the ordering costs are very high. We need to strike a balance between those by picking better quantities to order each time. Okay. However, we also have to be mindful that we have a constraint, okay, on space. That is, we only have so much space to accommodate each of these. Now, this is again where we're going to make a simplifying assumption. Generally speaking, the space required could be as much as the ordering quantity for every product multiplied by the space required per unit of the product, right? So if we ordered 10 product 1, each requiring 12 square inches, square feet, whatever that is, that'd be 120 we would need on that day, okay? If we happen to order all the products on the same day, we would need enough space for that maximum amount. However, we're going to just make a simplifying assumption and say we only will assume we need space for the average inventory amount. Okay, so I'm just going to multiply the average inventory by the amount of space required per unit and say that's how much space we'll generally be needing for product 1s. Okay, so that's a sort of simplifying assumption because we don't really know the exact quantity of every product on every given day in order to know how much space we're really using in total. All right, so if we sum each of those, we're going to constrain that to be less than 12,000 square feet. Okay? So that's our available space. So obviously, we have very small quantities that we're ordering, meaning we have very high ordering costs, very low inventory cost, and we're nowhere close to using up our space. Okay. What we want to compute as our objective is total cost, which would be the ordering cost plus the inventory cost for every product summed up. Okay. So the sum of all costs is our objective that we want to minimize. Okay, so we want to choose how much of each product to order at a time to minimize the number of orders so we can minimize ordering costs, but also minimize the average inventory so that we minimize the inventory costs subject to our space constraint. Okay, so these 4 rows here, 4 cells, are our decision variables. And the total cost computed here is the objective we want to minimize. Okay, and now for the first time we actually have a actual constraint. We want to constrain total space required to be less than or equal to the amount of space we know we have available. Okay. Again, so we are using the nonlinear engine. We don't need to automatically select. We know this is nonlinear, and we can solve. Okay? So, the optimal solution says something like this. We will order roughly 271 product 1s at a time, meaning we'll have, on average, 135 or so on hand, and so forth for all the products, for a total cost of $43,000. Okay. And it turns out the space constraint is binding. Okay? That is, it's possible we could have gotten a lower cost if we had more space available. Okay? That is, we might have preferred, in order to get a lower cost, to order even more per order to save on the ordering costs, even though that would have cost more in inventory costs. The savings in ordering costs could have been bigger than inventory costs, and we could have got an overall lower total cost had we had more space available. Okay. Just out of curiosity, let's do some optimization sensitivity. So I'm going to choose just this cell out to the right here and do optimization parameter. So we know we'll use as our lowest value 12,000, and let's say we could triple our space, maybe. So I'm going to set this available space here equal to that PSI opt param function. Okay, and now I can run an optimization parameter analysis, optimization sensitivity report to say if we had more space available, okay, let's do 21 points, then how much better of an objective could we get? Okay, and how much better, it's like I missed one, there we go. And how much better or how much different of a decision would we make on our ordering quantity? So let's run that optimization sensitivity. So this is going to tell us between 12,000 and 36,000 available square feet or units. How would our profit or how would our total cost change? Okay. Well, something certainly doesn't seem right here. This value didn't change at all. These did. All right. Let's go back and try that again. Set that equal to I18. It's PSI opt param. Did I? All right. I feel certain that I messed this up. So let's try this again. Optimization. 12,000. I think I put the 36,000 in the wrong place. All right. There we go. Same thing, try again. There we go. That does look better. Okay. So, what you can see is, so this is our space available. So, as space available increased, right, our costs started decreasing, right? We could get a better optimal cost by ordering more of, well, it looks like we ordered more of every product, okay, up to somewhere in the range of 13,200 to 14,400, because beyond 14,400 we made the same optimal decision. Okay, that is, even though we had the space available, it was no longer optimal to use all the space. Okay, because the inventory costs, ordering more and more, using up that space, started to outweigh the savings in ordering costs. Okay. So somewhere in this range is the sort of what we would call the break-even point, where any more space available doesn't matter anymore. That doesn't change our optimal solution. Okay. So it's interesting that some more space would have been helpful, could have lowered costs slightly, but not much more. Okay. That was that example. Okay. Let's do one more example for the night, and then we'll be done. So last nonlinear optimization example. This is another common optimization problem that you'll see, and it's one of optimizing investments in a portfolio. So investments involve, you investing your money and you get some sort of rate of return, some interest. So maybe you invested in a bank, in a savings account, maybe you invested in stocks, maybe whatever it is. You can invest in different things. They have different amounts of interest that they can return to you. Okay, it's not guaranteed always. Many investment opportunities like stocks may go up or they may go down. So you may make money or lose money. And they come with different amounts of risk. That is, how much money you could stand to gain versus lose could be different between one investment and another. Okay, so that's what I said. Investments have some rate of return, that is interest you earn. However, they may also be correlated. What you don't want to do is invest in two things that are highly correlated. such that if one of them increases in value, that is, gives you more return, more interest back than the other one does, but if one of them doesn't give you interest back, that is, it loses value, then the other one also loses value, right? Because then you're just gambling that they both go up, right? You can sort of hedge your risk by investing in things that aren't correlated, by saying, well, these two investments are both likely to go up, but if one of them does go down in value, then the other one isn't necessarily going to go down with it, and it might offset my losses, or I might even still make money, right, or make interest, or make a higher rate of return. So what we want to do is sort of choose how much to invest in several different investment opportunities, such that we either get the highest rate of return we can, the expected rate of return that we can, subject to a acceptable level of risk, okay, that we might lose money, a risk that things might be correlated and we might lose all of our money, okay? Or you can turn that around and do, let's find the lowest amount of risk we can take to earn a minimum amount of return. That is, I at least want to sort of assume, or at least try to average out earning a rate of return of, say, 5%. What's the lowest amount of risk I can take on by investing in the right things in the right proportions? Okay, so we're going to be given monthly return information on 5 different investments over 2 years. So 24 months of data for 5 different things you can invest in. From those 2 years of data, we'll be able to calculate the average rate of return and the standard deviation, which tells us what's the likelihood that we're going to get our money back plus interest, and what's the risk that we could lose some money. Okay. And then what we're going to compute is, first we're going to compute the overall portfolio return. So the total return is basically the sum of some proportion, how much we invested in each investment, I, multiplied by its rate of return. So each investment has its own average rate of return. If we invest 50-50 in 2 investments, then we basically just sum up 50% of each one, and that's our portfolio return. Okay, so proportion times rate of return by investment summed up. Now the risk gets a little more tricky. So risk involves basically pairing up every 2 investments, okay, and figuring out if they're correlated or not. It's something called covariance, which basically just says if one of these goes up, does the other one always go up, or maybe does it always go down? Okay, and we can compute how correlated they are. The higher that value, positive value, the more those things are synonymous. That is, one going up, the other one goes up with it. One goes down, the other one goes down with it. The larger a negative value of covariance, the more that one going up means the other goes down, and vice versa. So they're like negatively correlated. That is, you can invest in both of them, and when one goes up, your other goes down. When one goes down, the other goes up, and maybe you can average out a better rate of return. Okay, so the total risk of your portfolio is just the sum across every 2 investments of the 2 proportions, how much I invest in one I and one J, 2 investments, multiplied by their covariance. So how related are I and J to one another, those 2 investments. Okay, so those are the things we're going to compute. And then finally, we're going to look at a chart, a graphical representation that's going to show us sort of that best risk, lowest risk for each return, or highest return for some values of risk. Okay, so let's look at that. All right. So here we have the 24 months of data for 5 different investments. They have names in terms of what they're investing in. Okay. What we're interested in, so our decisions we're going to make are the proportion, how much we're going to invest in each one. Okay, so let's just assume, to start with, we'll invest equally 20% in each one. Okay, let's format those as, let's do numbers with 2 decimal places. And those are our decision variables. Okay, so that's our mix of, I want to invest 20% of my money in computers, 20% in chemical investments, 20% in power, 20% in automotive. So this is what we want to decide, what proportion to invest in each one. So now we can also compute average return, okay, for each investment. So for each month we have here the percent investment or percent interest earned. So in 1 month the computer investment earned 22%. Another month it happened to lose 1%, and so forth. So we just want to know, on average, how much return, percent return, did that investment give us? And so for computer, that works out to be about 2%. Okay, I'm going to format these just to make it a little easier to see as percentages. So an average rate of return. So each of them averages a positive rate of return, right? We wouldn't probably want to invest in something that on average loses money, but some of them average higher returns than the other. But we also need to know standard deviation, which is a measure of variance, which is, sure, we may earn on average 2%, but how confident are we that we're really going to earn 2% and not 5 or -1 or 10 or -5? Right? How much spread is there to how much that investment might earn or cost us? And in Excel, there's a simple standard deviation function we can use, where we just compute the standard deviation for every number, every percent earned across those 24 months. Okay. So now we know the standard deviation of each investment. So what this really says is, computer investments may, on average, will earn us 2%, but -9% from that and +9% from that is kind of the expected rate of return. So we might actually lose 7% or gain as much as 11% on these computer investments. Okay, some of these other investments have lower standard deviations. They also have lower average returns. So I can invest in something that's more reliable, lower amount of variance of spread, but that usually comes at the cost of a lower average return as well. So I'm not going to make as much on average, but I'm less likely to lose money in general. Okay. Now the last thing we need to compute is the covariant or the correlations, which are the covariances. Okay. Excuse me. Okay. And to do that, there is an Excel function for covariance named COVAR. Okay. And all we're going to do is we're going to take one column of data, comma, another column of data. Okay, so in this case, I'm actually going to compute the correlation of computer investments to themselves. Okay, and you'll see in a minute why I would do that. But basically, this says, obviously, when computers go up, computers go up. Okay. Now, I'm going to end up with a matrix of 5 columns and 5 rows because I want every possible pair, right, of investments and how they're correlated to each other. So the second column here will be computers correlated with chemical. Okay. So really what I can do is to make this and this absolute, and then I can copy the formula over 5 times And you'll see that in the fifth one, I'm computing the correlation or covariance of computer investment and electronic investment. Okay. Now, second row, I'm going to compute the correlation of, make sure I organize this properly. So second row, I'm going to use, the second investment, okay, as the thing I'll keep constant. And then in each column of the second row, I'll be comparing the chemical investment with every other investment, including itself. Okay. Third row, I'll be computing the power investment correlated with each of the other 5 investments, one by one. Fourth row, auto investment, with each other one. And lastly, the electronic investment with each other one, step by step. Okay. Now that's one way you can do it. This created a 5 by 5 matrix, but what you should see is that anything across the diagonal of this matrix is the same value. Okay, so the bottom left corner is the same as the top right corner. Okay, the value above that, and so forth. Okay, so each of these should work out. Doesn't look like necessarily they all do, just right. But each of these should work out to be close to the same thing each time, if I got the numbers right. Oh, but I moved that column too much. There we go. So those two values are the same. These two values are the same. These two are the same. These two are the same if you increase, there we go, and let it show all the numbers and so forth. So really I did more work than I needed to, but it was easy to create the formulas for this. Okay. Now, that gets us the covariances, or the correlations. So now what we need to do is we need to compute return, or we'll call it portfolio return. Okay, and the portfolio return is the average return of each investment multiplied by how much of our portfolio proportionately is invested in that. So this is just the sum product of our decision variables and the average returns. Okay. Portfolio risk. Okay. Remember, portfolio risk is going to involve the sum of every individual pair of investments, their correlation or covariance, multiplied by the percent of the portfolio invested in them. Okay. So the easy thing to do, the easy thing to do for that is going to be probably to say, take the correlation matrix value. In this case, this is the same investment. Okay. However, across the rows, across the columns, I'm going to keep where this whole row is comparing the computer first investment to every other one. So this portfolio risk, I'm going to hold the computer percentage static and drag that over. Okay. So now I'm just saying take each correlation matrix value, multiply it by the corresponding 2 proportion values for the 2 investments that matrix value represent. So the first row is always the computer investment, and then depending on which column it is, it's the other investment, okay, the other of the 5 investments, okay, and so forth. So I'll do that again. So this row times this decision variable, we're going to hold that constant, multiplied by that one, Copy that over. This row is the third covariance matrix value multiplied by the third row of the covariance multiplied by the third investment, and that's going to be our absolute reference. And then each column, each investment. Fourth row, fourth investment, held constant, multiplied by each proportion of each investment going through. And then finally, fifth row, fifth investment. Oops. That's absolute multiplied by this. Okay. And then ultimately, the portfolio risk is the sum of these things. Okay. So the portfolio rate of return, if I invested equally in every investment, would be an expected rate of return of 1.5%, and my risk okay, seems relatively small, 0.1%. Okay, that I stand to lose money because I've invested in things that will both reduce in value at the same time, effectively. Okay, so that's return and risk. These up here are decisions. Okay, so our model is going to be, let's see how we're going to do this. Our model is going to be to decide these decisions, how much to invest proportionately in each portfolio. Okay, and what we want to do is we want to find, let's say, the highest return we can get for a given risk value. Okay, so let's call that our risk ceiling, meaning we don't want any more risk than, let's say, 0.1%. Okay, so our objective is going to be the portfolio return. We want to maximize portfolio return. The constraint is going to be that our calculated portfolio risk must be less than or equal to the risk ceiling. That is, we don't want our risk overall to be more than 1.1%. What's the highest portfolio return we could get by investing in different quantities? Okay. Now, the only other thing we need to do here that we hadn't done yet is we need to compute the sum of all these proportions, and we all obviously need to constrain that value to always be equal to 1. That is, you can't invest more than 100% of your money. We don't want to invest less than 100% of our money, right? We have some money we want to invest. We want to invest it in these 5, maybe all 5 of these investments, in such a way that we maximize our return subject to a maximal risk. Okay, so let's solve. And does not support quadratic. Let's see what I did. Looks right. Open the Excel workbook that came with the book and use it. Obviously mistyped an equation somewhere. this should be roughly what they did. So they've computed every covariance of every pair. So the computer investment correlated with the computer investment correlated with the chemical investment, and so forth. They have their decision variables here as the proportions. So again, let's say we start with a base guess of equally weighted. Okay, they actually copy those proportions up here to make the equations down here work out better. So if you look at this equation, it's this covariance matrix cell multiplied by the proportion down here, because it's in the computer column, and multiplied by the same proportion as over here because it's in the computer row, and so forth. So if we look at, say, this one here, it's this value multiplied by this proportion for power and this proportion for chemical, and so forth. And then their total risk is just the sum of all those things. Okay? And their total return is just the decision variables multiplied by the average returns. Okay? And then this is the sum that they're going to constrain. So that looks like what I did, but let's try it here anyway. So the decisions are these 5 quantities. The objective is to maximize return. The constraint is that the sum of, actually they may already have, they already had all that done. So I was doing all of it, but so they're constraining G15, the sum of all the proportions, to be equal to 1. Their decision variables are B15 through F15. They were also binding, this may have been what I missed, they were also binding each of the decision variables to be less than or equal to 1. And then finally they were binding that the, let's do what we were going to do, which is C24, the portfolio risk is less than the ceiling. So let's try, we're going to do 0.1% highest risk. What's the best mix of investments to get the highest return? So let's try that. There we go. So it found that the optimal proportions were to invest the most in chemical, followed by power, followed by electronic, followed by auto, followed by computer, to get a risk of 0.1%, just like we wanted, that the highest risk we would accept, for the best return it could get, 1.39%. Okay. Now, you can also imagine, and what they've also set up is a constraint to say, let's imagine instead of maximizing return, we wanted to minimize risk, subject to the return being at least as big as something. So we want to earn at least 1.5% on average. What's the minimum amount of risk we would have to undertake, okay, to do that? So let's ask that question. So it's solved and found, okay, if you wanted a minimum return of 1.5%, I can get that with this mix of investments for a lowest possible risk of 1.22%. So two ways to ask related questions. Minimizing risk subject to the return you want, minimum return you want, or maximizing return subject to the maximum risk you're willing to take. Okay? Now, we could also, so let's take and do optimization sensitivity as a last step. And we'll go a lower value of 0.05 and an upper value of 0.2 for our risk ceiling. Okay, so we'll set that equal to this. We'll again make maximizing return our goal. Okay, and we'll ensure that the constraint we have set up is that we want our risk to be less than or equal to what's now being we're now doing optimization sensitivity on. Okay, so let's compute optimization sensitivity for that parameter. Let's do 16 data points. I think that sounds like what we'd want. And I'm just going to care about the actual return we get. So given this risk, we're going to change it from 0.05% to 0.2%. Given we're willing to take that amount of risk, one by one, what's the best rate of return we can get? Okay. Let that run. So best rate of return for different values of risk we're willing to take. So one thing we can note is it actually found that there's no mix of investments that can get you a risk as low as 0.05%. Okay, that's infeasible. So you have to at least accept somewhere between 0.06 and 0.07% risk. Okay? But what we can do now is graph these values. Let's do that one there. And this is the chart I was talking about, which is in portfolio investment circles is known as the efficient frontier. That is, it's saying for this amount of risk you're willing to take, here's the highest rate of return we think you could get, okay, based on average returns and computed correlations and everything, okay, which means, okay, if you're wanting a certain amount of return, you could look across here and figure out how much risk you would have to take on to get that. Or if you wanted to flip that and say, obviously, here's the amount of risk I'm willing to take, what's the expected rate of return I can see getting, okay? Now, just out of curiosity, we're going to graph the same thing. Except one small change. Instead of, we're going to switch the row, not switch rows and columns. That's not what I want. So we're going to graph. That's not what I meant. We're going to graph risks versus returns. So the opposite of what we graphed before. Okay. So same chart flipped looks something like this, which says on the x-axis here, if you want this much return, the y value is how much risk you'll have to take to get there. That is, you could take less risk, okay, so lower risk, but you're likely going to have to take less return. So you're going to have to live somewhere to the left of this line, right? Because this is the best return we think you can get for certain. Or I'm sorry, this is the lowest level of risk you can get, okay, for this rate of return. Now there's probably ways you can get the same rate of return for higher risk. So anywhere up and to the left of this is likely where you'll have to live. Sorry, can't get that to draw. On this chart up here, we're looking at sort of an opposite stance, which says the rate of return you can get for certain values of risk, you'll have to live somewhere below this line, meaning you can take the same amount of risk with a different investment mix and get a lower rate of return, but we don't think you can get ever above that rate of return. This is the optimal rate of return we think you'll get for any value of risk. So those things are called the efficient frontier, okay, or an efficient frontier chart, okay. All right, that's nonlinear optimization. The real key to nonlinear optimization is simply that it involves nonlinear functions, okay, with the caveat or the cost of you're never guaranteed the optimal solution, okay, the globally optimal solution. Generally, you can get a local optimal solution, so a very good answer, right, subject to answers nearby or close or similar, but you're not ever sure, you can't necessarily be sure that you've got the globally optimal answer. The only way you can work around that is to inject different starting answers from which the algorithm can start its search, start its hill climbing, or its gradient descending, or whatever, to find the optimal solution. You might find that starting from different places give you a different, maybe better, maybe worse, local optimum. Okay? And if you do that enough times, you can increase your confidence that you will find the global optimum. Okay. All right. Non-smooth operation or optimization. Okay. Now the good news is we're not going to do an example. The reason is there's really nothing different about non-smooth optimization other than it uses non-smooth functions for either the objective or constraints, which may involve functions like these: if, max, min. So they are functions where there's abrupt corners or even breaks in the graph. So you can imagine situations like thinking back to our economic order quantity example. You can imagine some sort of deal that the company might cut you to say, if you order a certain minimum amount of quantity, we'll actually sell it to you for a lower price. That is, we'll give you a discount subject to you ordering a minimum amount, right? So now our cost is based on how much we order, and there's some point at which ordering one more drastically changes the cost, right? So that's non-smooth. That is, there's a jump in that graph. There's a break in that smooth. It's no longer smooth. There's a break in that function. Okay. So any of these functions, or there are many others in Excel, if you use these, you're constrained to using a non-smooth optimization. The trade-off of non-smooth optimization is that you're never even guaranteed to find a locally optimal solution. Okay. All it can essentially do is look as hard as it can for as long as you will let it and find the best answer it can find. Okay? Because of these breaks or these non-smooth functions, the engine, the optimizer, can never be sure that one more change to some decision variable won't suddenly fall off a cliff, right, and find a new local minimum, or won't suddenly hop on top of a cliff and find a new local maximum. Okay? So all it can do is do its best to search around, not really doing hill climbing at all, and just trying to find the best solution it can find. Okay? That's the trade-off. So linear optimization, we're always guaranteed the globally optimal solution, but it's the most constraining. That is, every function has to be linear. Non-linear optimization is less restrictive with a little bit of a cost in that we can only guarantee local optimums, but we get to express more functions. Non-smooth optimization you can do with anything. Okay? Non-smooth optimization can literally use any kinds of functions. They don't have to be smooth. They don't have to be linear. I mean, you could certainly use linear functions or non-linear functions, but it can involve non-smooth functions as well. It's just guaranteed to only find good answers. Okay? Not best, not locally optimal, just good ones. Okay? All right, are there any questions about nonlinear optimization? All right. I will post assignment 6 probably tomorrow, so you can get started on that. It will involve nonlinear optimization problems. We will not focus on non-smooth optimizations. Okay. Again, you're welcome to look in the book. I forget if it's chapter 11 or where it is. If you want to learn more about it, as far as building the models, it's just a bigger suite of functions we can possibly use. Okay, when we build our model, we can use max, min, round, V lookups, chooses, H lookups, all sorts of strange things. And in the end, it's the same buttons you click, and it's the same approach to building the model and finding the optimals or the optimized solutions. Okay, you're just not guaranteed if it's really optimal. So we won't bother with doing examples of that. If you are interested, you can look in the book or you can talk to me, and I'll be happy to talk to you about it. Okay? Well, that's it for tonight. We'll end. Thank you for